Good morning, everyone. It's a real pleasure to have you all in your living room. As for myself, I am also in my living room. As you can see, there are couches behind me. So it's a real pleasure today to announce our first guest, Professor Yehuda Lindell. Yehuda Lindell is CEO of Unbound Tech and also professor at Bar Ilan University in Israel. Yehuda attended his PhD at the Weizmann Institute of Science in 2002 and spent 2 years at the IBM Tate G. Watson Research Lab as a postdoctoral fellow in the Cryptography Research Group. Yehuda has carried out an extensive research in cryptography and has published over 100 conference and journal publications, as well as one of the leading undergraduate textbook on cryptography. And just a side note, it was my textbook on cryptography and I spent a lot of time reading it. Yehuda has presented at numerous international conferences, workshops, and university seminars, and has also served on program committees for top international conferences in cryptography. In addition to Yehuda's notable academic work, he has significant industry experience in the design and deployment of cryptography in a wide variety of scenarios. It is a real pleasure to have you, Yehuda. Please proceed to your talk and have fun. Thank you.
Okay, thank you very much. And I want to thank the organizers for having me. It's a great opportunity and it's really great to be able to get this done in these times. So I'm sharing the screen and I hope you can all see it. So I'm going to talk about, the title is The Path to Software-Defined Cryptography via Multi-Party Computation, or really how we can protect cryptographic keys in software in a way that actually provides strong guarantees. So just as some context to the talk, cryptography is a central tool of computer security. There's a lot more to security beyond cryptography, but it's something that is very central to it and crucial to it. And all of cryptography, as we know, relies on secrets. If you want to do key exchange or encryption or digital signing or want to do authentication, you need to have some secret. And that secret is what differentiates the attacker from the legitimate users. So once such a secret is stolen, then all security is lost. It's really a Boolean situation. If your key is well protected and you're encrypting well, then you're secure. And if the attacker steals the key, then there's absolutely zero protection. And not only is it zero protection, it also becomes the easiest attack possible because, in fact, once the cryptography is broken and you can break the crypto, then you can actually attack typically via the allowed API, and that goes undetected. So this is different from other types of attacks where the attacker has to behave in an anomalous way, and hopefully we can catch them. When the cryptography is broken, it often becomes just the easiest vector of attack. And that means that we need to protect the keys. We need to protect them in a strong way so they don't get stolen. And the legacy solution was simply hardware. So you have HSMs, hardware security modules, you have smart cards, you have one-time password tokens, and these are supposed to be very secure boxes that prevent the key from being stolen from them. Actually, the vast majority of effort into these is around physical security, which is somewhat strange today because very often HSMs sit in very secure data centers. But in any case, these are supposed to prevent the key from being extracted by having a limited API that will only do cryptographic operations and nothing more. And even leaving aside that the security of these actually is not perfect, and if you just want to see one example, look at the talk at Black Hat USA last year by Ledger about a complete break of an HSM. It was also at the Real World Crypto Conference in January this year. But even leaving that aside, having these physical anchors when everything is virtual brings many difficulties. The entire computing world has moved to software, virtualization, containers, cloud. And that's because there are no more problems of procurement, and you can remotely manage them, and there's a cloud economy, and you can have a single interface and environment across whether you're in your data center or in a cloud. and so on and so forth. And therefore, these hardware anchors actually are a huge pain when it comes to providing a strong cryptographic infrastructure for an organization. And the question that we're asking is, what if we could move to software? Now, obviously, you could move to software, right? I mean, just instead of having an HSM, take that same type of code and put it in a virtual machine and you're done. But of course, what we're really asking is, what if we could move to software in a way that would still provide a very high level of security, a comparable level of security, if not even better? And that would remove one of the big obstacles to deploying a strong and usable cryptographic infrastructure in organizations. And the approach that I'm going to present in this talk is that of using secure multi-party computation, or MPC. This is a well-researched subfield of cryptography. Research began actually in the late 1980s. There have been literally thousands of research papers about it. It spent a long time being in the realm of pure theory. I would argue that for the first 2 decades of its life, it was pure theory. I started researching it in 1998 in the beginning of my PhD. And I fully admit to being a pure theoretician and enjoying it very much. How to define security, how to prove security, what assumptions are needed to get security. As time went on, and particularly in the last 10 to 15 years, it's actually become a very applied area of research. A lot of MPC research today is not only published in the cryptography conferences, also in the security conferences, and things like ACM-CCS, which is one of the best academic security conferences. You'll see a lot of MPC research. And the idea of MPC is that you can compute on private data without revealing anything, something which sounds like a bit of a paradox, like a bit of an oxymoron. How can you compute on something without actually seeing what you're holding? So I actually want to start with a toy example and then go into more details later on. And how this actually connects to the notion of protecting keys is something that we'll get to after we understand what the notion is itself. So the toy example that I'm going to give is we have three cryptographers, and they want to compute their average salary, but without revealing it to anybody else. If you can actually see the salaries here, they are so low that they're just embarrassed to tell each other. And they're cryptographers, so anyway, they're paranoid and don't want to tell anyone their salary. And maybe they want to do this so they want to know, are they earning below average or above average? Of course, if they're earning below average, they'll be outraged. If they're earning above average, they'll just think, yes, that's because I'm a better cryptographer. But in any case, we have Alice, Bob, and Eve, and how can they work out their average? So the first step in this toy example is that Alice is going to choose a very large random number. Let's say 652,195. And exactly the domain, I don't want to go into the details. The domain of where you choose this actually makes a difference, but let's just assume it's a very large random number and much larger than their potential salaries. And then Alice will just add that random number to her salary and send it to Bob. So Bob gets this number, 772,195. And what I want to note before we continue is that from this number, Bob actually cannot know anything about Alice's salary, or essentially almost nothing about Alice's salary, because the large random number drowns out the salary. If Alice's salary is 80,100 or 140, and you're choosing a random number from a large enough domain, then this will actually look exactly the same. So Bob gets this number, but doesn't know anything about Alice's salary. And what Bob does is takes the number and adds his own salary to that number and sends it to Eve. So Eve now again gets 877,195, which is just the number that Bob got plus his own salary of 105,000. Once again, Eve looks at this number and says, well, it tells me absolutely nothing, because Alice's original random number again drowns out the actual salaries in there. And Eve does the same thing. She now adds her salary to that 65,000. Eve is the unfortunate cryptographer with the lowest salary, and she sends that over to Alice. So Alice gets the number 942,195, which is essentially the random number that she started with plus the sum of the other three salaries. So she can just subtract that random number and divide by 3, and she gets the final result of 96,666. And what I want to argue is that nobody learned anything. We already talked about why Bob and Eve didn't learn. They didn't learn anything because all they saw was a random number. Essentially, the salaries that were there were drowned out by that original random number. Alice, on the other hand, gets back something that actually has the sum of the salaries, but nothing beyond that. And she can't determine anything beyond the sum of Bob and Eve's salary because she just gets it in one number. And we know that the average and the sum is actually the same. It's just multiplying or dividing by 3. Therefore, this reveals nothing more than the average. And no individual has learned anything but the average from this procedure. And this is a protocol that's actually secure up to one party being corrupted. If 2 of them want to collude against the third, well, in that case, anyway, you shouldn't be computing the function because it will reveal it. But this just gives you an idea that it's actually possible to compute on data without revealing anything whatsoever but the result. And that's a very powerful paradigm. And I want to stress that in the late 80s, when this was initially researched and going forward, it was actually shown that you can compute any function that you want. Now, I'm not saying you can compute it efficiently, that actually can be run in practice, but you can actually compute any function that you would want in a secure way. With more detail, the setting of secure computation is one where you have parties with private inputs, and they want to compute a joint function of their inputs, but ensuring that nothing but the output is learned. And we call that property privacy, and also ensuring that the output is correctly computed, which is correctness. And you could think about many applications for this, comparing DNA, comparing databases, carrying out SQL on SQL queries on databases that are held by different parties. You can think about set intersection. I want to compare what contacts are on my address book versus somebody else's without revealing anything but the contacts in common, or even without revealing anything about how many contacts we have in common. And there are many, many applications for secure computation. One thing which is important to understand is that these properties should be guaranteed even if some of the parties are adversarial, so they're cheating. And there are two main classes of adversaries. One is a semi-honest adversary. That such an adversary actually runs the correct software, but tries to learn more than they're allowed to by looking at the transcript. That's a relatively benign adversary in the sense that they actually are not trying to actively cheat, and they can model some things like inadvertent leakage. But in general, we much prefer to talk about malicious adversaries, where the adversary can actually run any software that they want. They cannot, and they should not be able to learn anything. And even if they know all the protocols being used and the design and so on and so forth, we actually can guarantee that they're unable to learn anything, no matter what attack that they run. And furthermore, given that this notion rests on a strong theoretical foundations, the security is mathematically proven. So we actually have a mathematical proof of security that nothing can be learned. Of course, we have to be sure that our proof doesn't have any bugs. We have to be sure that our implementation is implementation follows the actual spec, but that there are already orthogonal problems that exist everywhere. And now what I want to argue is that we can use MPC in order to protect keys in software by moving from this sort of centralized trust model where a key sits somewhere. And if the key is sitting in secure hardware and that truly is secure, then okay. But it has all of the functional and operational and other problems that come with it. But if it's sitting in software on any single machine, then it becomes a single point of failure that if you steal that key, then you can lose everything. And basically what we want to argue is that we can use MPC to build a distributed trust model where keys are shared amongst multiple machines, but using a type of sharing so that no subset of the keys actually reveals anything whatsoever. So a subset of the shares just looks completely random. You'd actually have to have them all. And further, the shares are never united even in use. So it's not like, okay, we bring the shares together for one tiny fraction of a second to do the operation. We don't want to do that, because if that happens, then at that point, it's actually vulnerable to being stolen, and you have, again, the single point of failure. But using MPC, it's never brought together, and even if a subset are corrupted and controlled by an adversary and who has full, can run malicious software, etc., they still cannot learn anything. And the protection level you get is based on strong separation. I'll give you an example of that later on. Another advantage is mitigation against insider threat. If you split a key into even just two pieces and you have different administrators, now no longer do you have any administrator having access to the key, and that's a big advantage. So to sum up, like how we can get this, so you can think about splitting a key into two pieces. Each share is just complete random garbage without seeing the other one, and we'll see later on in the talk how actually this can work. And you can store these shares on separate locations. And not only that, you do something called refresh, which means that you change the sharing very frequently. So the key itself stays the same, because changing keys very often is extremely painful and not practical, but the sharing itself can change. And then what that means is the attacker would actually have to breach both machines at essentially the same time before a refresh happened in order to learn anything. Again, I'll go into that more detail later on when we see the actual example of how this can work. The keys are never combined, and in fact, it even can be generated in a way that's distributed, so they were never at any point in their entire life cycle from generation through use, the key was never in any single place at any single time. And again, mathematically proven security properties, so we're not just waving our hands and hoping for the best. We're actually resting on strong theoretical foundations from decades of research. So I just want to give an example of how you could deploy such a, we'll call it a virtual HSM, how you could deploy such a thing in a way that would actually make sense in a real scenario, a commercial scenario. So think about an organization that wants to be both on-prem in a data center and also in multiple clouds. Then they could take, and let's assume we're splitting a key into two pieces. So each key is split into two shares. And then we have a pair of machines, which one we call EP and the other we call P. So EP we call entry point and the other we call P for partner. And the entry point is the machine that actually gets the request to doing a cryptographic operation. So this would be the same feel of a network HSM, or you use a standard library, PKS11, Java Crypto, or Microsoft CMG, or OpenSSL, or KMIP. Any of those can be fully supported. The entry point gets the request for cryptographic operation, and now runs MPC with its partner and returns the result. The key never ever being brought together. So in this specific configuration, you can see that you have one pair split between the organization's data center and AWS. The second pair being split between AWS and Azure, and the third pair being split between Azure and the data center. What this gives you is a combination of very high availability, and robustness. You would need to have more than one cloud and a data center go down. So you need to have 2 out of these 3 going down, and that's very, very unlikely, especially because you can replicate this, of course, amongst multiple regions and locations because it's all software, so there's no problem just having automatic replication. That's first thing. And secondly, the attacker has to simultaneously breach 2 completely different settings, 2 completely different scenarios, and that's very, very difficult and even a little bit hard to imagine that it could happen. And especially they have to be resident simultaneously on both. Of course, there's no perfect security, and if the adversary can do it, then this theoretically can happen, but it's very, very hard, almost inconceivable, to breach such different scenarios, such different settings at the same time in order to be able to gain any key information. Of course, all of these machines are further hardened, and you do all of the standard measures that you would do anyway. But this shows you how such a deployment could work. If you have this separation and you can do this MPC, then you would get something very strong, very powerful with high availability, disaster recovery, replication, and all in software. Give you another example of how you could use such a thing, and then we'll get to, okay, but how does it actually work? And we are going to get to that, I promise. So let's think about the fact we wanted 2-factor authentication. We have these mobiles, they're powerful computing devices, and we are using these actually for 2-factor authentication. There's Google Authenticator, there's Microsoft for Office 365, and there's Salesforce, and there's others. But these devices are all extremely vulnerable. So the key sits on the device. If an attacker, if malware is installed on the device, and that's not very difficult to do because half of the apps in the App Store are actually malware, especially in Android. But iOS also has its problems. Then the key is vulnerable and you can steal it and then obviously bypass everything. So how could we build like a virtual smart card or a virtual one-time password token on the mobile and not have to have these physical devices, but still get security? So the same idea exactly. You split the key shares, not between two servers, but you split the key shares between a mobile and a server, and you carry out the computation via MPC. And that way, the key is never present on the mobile at any time to be stolen. Because even if there's malware and you can run malicious code, etc., you cannot learn anything about the key. Furthermore, the refresh can actually take place at every single operation and at frequent intervals. And that gives you strong anti-cloning and detection, because if somehow you could get a clone of the machine, then the clone and the real device would go out of sync. If the real device used the key first, then the clone would be complete garbage. And if the clone used it first, then the real phone would fail, and we would actually have full detection of that an attack took place. And that's something which you typically don't get with hardware solutions. You can also audit not fully everything at the server, because you require a server to do the operation. You don't have full visibility into all operations because you're auditing in both places, and that obviously is very important for a security perspective. And finally, it's easy to use because it's on a mobile, and that is something that everybody always has, and you don't need special hardware. You don't have to worry about delivering it and procuring it and so on and so forth. And it's also a security advantage because people will leave their smart cards and one-time password tokens lying around, but nobody will leave their mobile anywhere lying around. And if their mobile is stolen, they will know about it very, very fast. Okay. One final advantage, which I think is really important to talk about, because this now goes a level beyond what you can do in using other technologies, is moving from key theft to key misuse. The standard model for key protection for cryptography is preventing the key from being stolen. And if you have a database of 10 million credit cards and they're all encrypted, and the attacker can steal the key, obviously they steal all 10 million credit cards, and that's a disaster. If they can get to the machine that acts as the HSM, then they can ask for decryptions, and maybe they can do 10,000 before they're caught. And that seems, that's okay. It's not the end of the world. So key misuse is not prevented, but it's not too bad in that application. But there are many other applications where key misuse is a disaster. For example, code signing. A single malicious signing by an attacker is a complete failure. For example, it can be the ASUS firmware, which is corrupted, and now you can infect many machines. It can be a banking application, and it's not enough to protect from key theft because I just need one signing operation, and I can now deploy a malicious banking app that customers will accept as being valid. So using MPC, we can split a key not between two machines, but actually between multiple machines. And we can define flexible quorums that will say, for example, you need 2 out of 3 parties at R&D and 1 out of 2 at legal to approve the code signing operation. That this actually has gone through everything you need. In fact, you can have arbitrary size sets and numbers of sets, and you can set up really elaborate business processes that are actually cryptographically enforced. And this is what's really important. All of these parties actually participate in the MPC, so it's not that you can bypass them and get to the machine that does the signing. If they don't approve, they actually hold cryptographic material, and even if you get to the machine that does the signing, they can't do anything because the key actually is not even there. And you can set the quorum sizes to be smaller or larger depending on need, and get very, very powerful key misuse protection. All right, so now that's really all the background on why we want to do such a thing and what value we can get. And I want to stress that these are not theoretical, but these actually things exist and are running in production and are being used around the world already today. So this is not just something that can be done in theory. Actually, it's possible to do this in production and get very good performance. What I want to show you now is how this can actually work. And I'll start with a friendly, fun problem and then get more into some math. So I'm going to talk about the dating problem, something that the introverts amongst us may recall our days in high school. And let's say that you want to ask somebody out. A guy and a girl want to check if they're both interested in going out, for example. And if they both are, then I would like to hear yes. But if at least one of them is not, then the output should be no. Right? So if I was interested and someone else wasn't, then the result should be no. And why does that help? Because when I ran this with Alice, Alice said no, and I said yes. The result came out no. Alice actually doesn't know that I said yes. Right? As far as Alice is concerned, it may be that I said no as well. So you could think of running this between all pairs of students in the class or something, and then nobody loses face, and we're sort of protected, and we don't mind telling the truth about whether we'd be interested in doing this or not. Technically, actually, you can see that what they're actually doing is computing the AND gate. So we can actually do this with cards. Alice and Bob each get 2 cards. And by the way, the reason why this is interesting beyond what we showed before about the salaries is because the salaries have, you know, it's numbers. You add them. They're in a nice algebraic structure. But this is something, an AND gate is something that it seems more difficult. So let's see how it works. So Alice and Bob each get 2 cards. If Alice likes Bob, she puts the king first and the ace. And if not, she puts the ace first and the king. And Bob does the same thing, but in reverse. If he likes Alice, he puts the ace and then the king. And if not, the king and then the ace. And I know that anybody looking at this is going to say, I don't know what you're talking about, but bear with me, you will in a moment. Then each turns their card over and they put an ace in the middle. Okay, so Alice puts her cards down, Bob puts his cards down, and we have an ace in the middle. And we note now that if you were to turn them all upwise, then if Alice and Bob like each other, you get a king ace. That's Alice's order. The ace in the middle, and then Bob's cards, which is an ace and the king. So you have 3 aces in a row. But if they don't like each other, then it's going to be one of these 3 configurations. And what you can see that all of these 3 configurations are actually exactly the same up to a rotation. So there's always 1 ace, a king, 2 aces, and a king. Even the third one, the third configuration here, it's also 2 aces in a row because the first and last are actually next to each other when you think about rotation. So what that means is the parties will turn over the middle card and then randomly rotate. So Alice will pick it up and rotate. Bob will rotate and they'll open it up and look, are there 3 aces in a row up to rotation, or are there only 2 aces in a row up to rotation? And they'll know whether they're going out for a date or they're not. And the point is that because the 3 configurations which relate to either Alice saying no, or Bob saying no, or both saying no, all these configurations are identical, so actually they have no idea which one is the correct one, and all they know is that at least one of them said no, but they don't know if it's 1 or 2. And therefore, even introverts can solve the dating problem without losing face, and hopefully we can help introverts out. But let's come to something which is more serious, which is how can we compute the RSA function? So I have all the modular notation in here, but really you can just ignore it. It's not important whatsoever for the understanding what's happening here. So in RSA, the private key is a modulus n and an exponent d, and the public key is a modulus n and an exponent e. And the private operation, either for signing or decrypting, is just to take some value y and raise it to the secret value d. Okay, and if it's decryption or signing, that will change what y is, but the operation, the secret operation, is raising to the power of d, and that d is the private key that has to be kept secret. So the first thing we want to do is share this value d between 2 servers, S1 and S2. So S1 can just choose a random d1. It's a random value, and server S2 will get d2, which is d minus d1. The mod here is 5 and not n for technical reasons that I don't want to go into here. And what you can note is that d1 plus d2 equals d. Okay, so they hold 2 random values that sum to the real secret key. And the security just at this stage to note is that D1 actually reveals nothing about D because it's just a random value. It's a random value completely independent of D, so obviously it can't reveal anything. But D2 also reveals nothing about D because D1 completely hides it. In fact, D2 you can look at as like a one-time a pad encryption of D, and so each server, S1 or S2, having D1 or D2 actually know nothing whatsoever about the key D. And now we have this situation where they hold additive shares. We call these additive shares of D. And you can compute the private operation y to the power of D by S2 computing just y to the power of D2, S1 computing y to the power of D1, and then multiplying them together. So just multiply these two public values now, Z1 and Z2 together, and verify that it's correct. And what you can note is that because you're multiplying two values that have the same base and different exponents, you're just adding in the exponent. And when you add in the exponent, then you get that from y to the D1 times y to the D2, you get y to the D1 plus D2, which equals y to the power of D. And so they've actually computed the correct operation, but neither of them saw the full key D. So each one just did a local operation, and we combined it together, and nothing was revealed. In an actual deployment type scenario, you can think of two servers holding D1 and D2. Some client wants to do some decryption. It sends a ciphertext. The first server, which, for example, we call the entry point in that cloud configuration, sends a ciphertext to the second server. The second server sends back what we call a partial decryption, which is Z2, which is y to the D2. And the first server then computes again y to the D1, multiplies them together, and sends back the result. One thing that I want to set just to stress is that we actually have formal definitions about what security would mean here, and that nothing more is revealed about the key than the result. And we can formally prove this protocol according to that definition. I'm obviously not going to kill you with those details here, but actually you can write a formal definition and a formal proof that this protocol reveals nothing more than you would get from just getting the pair of ciphertext and plaintext. So if RSA is secure, then this protocol is also secure. And this holds even if one of the servers is corrupted and you have an attacker running malicious code, they cannot learn anything at all. Well, what about the refresh? As I mentioned, we want to change the sharing of the secret frequently, and we'll see in a moment why that is actually very helpful. So we have two servers that are holding D1 and D2, and they can do coin tossing. It's another MPC protocol to get a random value R that neither can influence. And then the first server can compute D1 prime, which is D1 plus R. The second can compute D2 prime, which is D2 minus R. And then note that D1 prime plus D2 prime actually also equals D, because you're just adding R and subtracting R, so you actually haven't changed anything. And then I hold a different sharing of exactly the same secret. So nothing, they can still continue working. But if an attacker stole D1, and then later on, a month later, managed to breach the other site, and they were no longer in the first site, and they stole D2 prime, all they would get would be a pair of values that sum to complete garbage, because D1 plus D2 prime has this additional R value in there, and nothing is revealed. So that's why we do this at frequent intervals. And this is something called proactive security in the academic literature, and we call it refresh here. So this is pretty easy. You might be looking and saying, okay, that's not so, it doesn't look so difficult. And you're right that RSA is very easy because it has really nice algebraic structure. Elliptic curve Diffie-Hellman and ECDSA are harder, but they're still not too bad. The real question is, how could you do something like symmetric encryption, or HMAC, or something that, AES and these functions are just complete chaos. They're permutations, table lookups. They have no algebraic structure at all. How could you compute this? And the answer is we can use something called a garbled circuit. So we actually take those functions and we represent them as a Boolean circuit. So going back to the beginning of undergrad computer science in discrete math courses or in computability courses, we can represent any functions of Boolean circuit, and then we construct an encrypted version of the circuit, and we can evaluate that encrypted version without revealing anything but the result. And I'll show you how that works now. So this is a simple AND gate. Input wire is UV, output wire is W. Here's the truth table of that gate. So 1 and 1 goes to 1, everything else goes to 0. And the first step is to actually replace all of the 0 and 1 values by symmetric keys. Okay, so KU0 and KU1 represent 0 and 1, and likewise K0V and K1V. But we can't give you this table because in the third column you can see that there are 3 values that are the same and only 1 is different, and you automatically know that they are the 0 value versus the 1 value. And of course, this holds even if you permute the order of these rows randomly, you would still be able to learn. But I can give you 4 ciphertexts in random order. And if I give you these 4 ciphertexts, if you have 1 key for the U wire and 1 key for the V wire, you would be able to decrypt exactly 1 of the ciphertexts in the output. So for example, you had KU0 and KV1, you could decrypt the second ciphertext. This will be in random order, so you wouldn't know that it was the second one. Nothing else would correctly decrypt. But you would have no idea actually what you've computed because they all just look like random garbage. KU0 and KV1 look like random garbage, and KW0 is random garbage. So you've actually computed something completely obliviously without knowing what you're doing. How can we now use that idea to garble an entire circuit? So we have some circuit representation of a function. So we do the same thing. We write random values on each wire, and we build 3 of these tables, which actually, again, each one is in random order. For here, it's not. We build a table which provides mappings from the inputs to the outputs. And we also provide a output translation table, which enables you to map. You want to be able to map the values at the end into what the actual output is. This will become clearer once I actually go through how this computes. So now let's say we have the input of 0, 1, 0, 1 and want to compute the circuit over 0, 1, 0, 1. Then what I can do is I can give you the key for the 0 value on the first wire, for the 1 on the second, the 0 on the third, and the 1 on the fourth. And I give you these 4 values that just look like random garbage. And I tell you, now I want you to compute the circuit. You don't know what you're computing, but you could do the following thing. You know KB1 and K0C. You don't know whether they represent 1 or 0, but you have these 2 values, and you can go to this table and you try to decrypt one at a time, and you end up decrypting the 3rd row. And now you actually are able to decrypt only that value, and you get this K0E as the output. You don't know what it represents, but you have this value, and now you can see that you have KA0 and KE0. You do the same thing. You decrypt. You try decrypting each one. You only succeed on the first. You get that output value. Likewise, you now have KE0 and K1D. You manage to get the second value here. Then you get K1G at the top here. And now you go to the output translation tables and you get 0 and 1. And what I want to stress that what's happened here is you now know the output is 0, 1, but you actually don't know what the input is. The input could have been indeed 0, 1, 0, 1, but it could also have been 0, 0, 0, 1 or 0, 1, 1, 0. All of these would lead to the same output, and you would actually have no idea which input it is. And this might seem incredibly expensive, and indeed the AES circuit has about 20,000 gates, but with many optimizations, you only need to send these for about 5,000. And we can do this entire thing in under a millisecond. We can actually construct a garbled circuit, and we can evaluate one in under a millisecond. And that's how you can compute even symmetric functions like AES and even ASGCM and HMAC, also in MPC, even though they have no structure whatsoever. An interesting thing to note is this is a protocol dating back to Yao in the mid-80s, in the mid-1980s, that was a purely theoretical protocol at the time, but given with many years of optimizations and algorithmic and cryptographic improvements, it's actually something that's in use and in production today, which is an interesting win for theory in my mind, and showing that theoretical research does have, especially in cryptography and in many fields, does eventually pay off and become something practical. I'm running out of time, so I'm going to skip a couple of things here. I just want to note that using this, you can really virtualize cryptography, get something that supports business needs, has improved management operations because it's all in software, and without giving up on security, because MPC gives you proven guarantees. You can certify it via FIPS, and it's transparent and agile because it's software, and that's a lot of things that we're looking for in cryptographic solutions. So thank you very much, and I'll open it up to questions.
Professor Lindell, it was a real pleasure to listen to your talk, especially for me, which have a special inclination toward cryptography. So we will start asking questions on the Slido app. People will still have time to ask questions. So as we said on the Twitch chat, we can upvote questions if you feel the question is relevant or if it's close to the questions you wanted to ask. Otherwise, feel free to ask questions. So without further ado, let's start with the most upvoted question. What has been implemented for large-scale data pipelines? So we know big data is a thing now, and people have to learn stuff from on a large scale between potentially conflicting enterprise. So can you tell us
for
about
MPC in large data scenarios, that's actually more difficult. In other words, we can actually use techniques to compute essentially anything, but on very big data it becomes much more challenging. So when you want to compute smaller operations like cryptographic operations, that's very efficient. We do have efficient protocols for things like set intersection. We can compute the intersection between very large sets. In fact, Google uses this for validating how much people should pay for advertising based on how much advertisements convert to actual purchases. You can do quite interesting things for SQL on data that's separated. And there's been quite a bit of work in the academic community around doing learning, so federated learning or classification, but more if you have a model and you have an example and you want to verify, you want to get a result on that example without revealing it, these things actually are very efficient. But you shouldn't think that, oh, okay, wonderful, now I'm going to run MPC on the Facebook graph and be able to have a social network that is fully private. That would be much too slow.
Yeah, thank you. Yeah, I saw that Google released a private join or an intersection of datasets. I think that's using some kind of the techniques maybe that you discussed, but maybe not the garbled circuit model. But
yeah, so they use MPC. They use actually a version of set intersection which is based on elliptic curve Diffie-Hellman, that's sort of the underlying technology. There are actually much more efficient methods today. They wanted to choose that because it's very simple, which has other advantages. But there are many different techniques, and we can do set intersection very, very fast today.
Perfect, thank you. So next question. In many industries, any cryptography use will depend on its acceptation from standards. What is the status of standardization for the cloud implementation?
So the point here is that MPC only changes the way you compute the function, but we don't change the function at all. So we can provide the full standard crypto API that you're used to. It's FIPS 140-2 certified, so it's all NIST-approved algorithms. And therefore, actually, there is no problem in adoption because you can look at this and work with it as you would with any other standard cryptographic library. It's just that you're getting protection in software rather than not protecting or in hardware, and that's the big advantage. But there is no, I think, as a cryptographer, the last thing I would tell anybody to do is to use a proprietary cryptographic scheme or something else. No, we only want to use the standard schemes, and MPC enables you just to compute it in a way where the key shares are separated, but the algorithm is the same standardized certified algorithm that everybody accepts, and therefore it's not a problem.
Perfect. So just a side question to this question. In your opinion, what what is preventing large-scale adoptions of such technologies right now?
So I don't think that it's being prevented. It's actually, there are companies, Ambatek is one of them, who are actually doing this. It's new technology. There is, we need to educate the market, but the market has heard much more about MPC today. And we actually see these things are in production quite significantly. It hasn't yet taken over the world. We hope that will happen. But it's not the situation of 5 years ago anymore. These are actually being used already quite significantly.
Perfect, thank you. So the next question is related. How much work is still research work versus development? It's a quite open-ended question.
Yeah, so I actually think that it depends what you're looking at. If you have a very specific problem that you want to solve, and there is enough knowledge and expertise out there to do it. But it's still a technology that requires higher expertise. It's not like, even to be honest, even implementing anything cryptography requires expertise, right? If we ask someone, an undergrad student who hasn't taken a course in cryptography just to encrypt, the chance of them doing it right are very small. But this is very, very difficult and requires really high expertise. But if you have a specific problem, depending on the size of the problem, there are actually quite good solutions. In order for it to really be something that is ubiquitous as a technology, a lot more research is needed to really fill in the stack going from programming languages, so having languages that enable you to write code that have private and public variables, and when it's private, it runs an MPC, and it will know which protocols to use, and there'll be guidance on how to program such a programming language in a way that's friendly to MPC. There's a lot of research still to be done, and there's a lot of research, it's a very active area of research, also pushing it faster and faster, which is important because as we want to be able to solve more and more problems, and the more efficient it becomes, the more problems we can solve. So there's certainly development, and there's certainly a lot of research to be done. I think there'll be decades of research still to come in MPC, and in fact, even more. But it's already at a stage that's certainly mature enough for real use in production.
Perfect. Yeah, let's hope people keep on researching if it becomes so ubiquitous. So next question is a bit more technical. Does amplifying elliptic curve and iterating more time bring stronger quantum resistance, as we do by raising iterations on prime numbers factorization?
Good question. Even there, there's discussion in the community as to how effective taking very large primes would be against a quantum computer. Currently, we don't know. There isn't really enough understanding because the number of qubits you need in a quantum computer depends on how much error you have. There are different models. Personally, I think that just taking if someone really builds a quantum computer that can scale and break crypto, and I think I'm in the if camp, not a when camp. I don't think it's necessarily we know the answer, but if that actually happens, I would probably be nervous about using something that just raises the size so that it's beyond the current state of the number of qubits. But there are other things out there. So for asymmetric cryptography, we have lattices, we have isogenies. There are other solutions. Coding-based crypto. Right now, I think if really people are worried about quantum, they should just make sure the crypto is agile. They can switch out algorithms quickly because it's still years away. I don't think that most people need to be really concerned yet about changing algorithms.
Yeah, perfect. Thank you. So it actually brings us, maybe the question was partially answered, but how confident are we that the cryptographic primitives that you described, so mainly the garbled circuit model, is quantum resistant? So
the garbled circuit model, for example, only uses the actual garbled circuits uses symmetric encryption only. So if you take AES-256, the best of our understanding, that's quantum resistant. In the protocols themselves, there are other elements, but they can all be made quantum resistant. So you can use lattices for oblivious transfer and other elements that you would want in a protocol. These MPC can work also in a post-quantum setting.
Perfect. So it's basically reduced to the Grover search algorithm.
Exactly. Yeah. So obviously RSA itself wouldn't be secure anymore. The MPC protocol for RSA that I presented is as secure as RSA. Just the fact that RSA isn't secure anymore means that it's meaningless.
Yeah, perfect. Thank you.
Of course, you could.
So the next question is talking about RSA, specifically about the example that you gave. In the RSA refresh scenario, where we exchange a R, should R be secret from an eavesdropper?
Yes, it should, because if an eavesdropper saw R, then they could steal D1. If someone got into the first computer and stole D1, and then just eavesdropped and saw all of the R's, then they would actually be able to keep up to date with the refresh. Whereas the whole point of the refresh is so that if you stole D1 or D2, stolen one of them, and you didn't know a single refresh value, just one refresh value, then it becomes completely useless. For someone who hasn't stolen one of the Ds, it makes no difference, that R. But in general, the best practice is all of these protocols are run over mutually authenticated TLS, so this isn't an issue.
Perfect, thank you. I think this is all we had as time for questions. I see the cues that we're running out of time. It was a real pleasure to have you, Professor Lindell, and I had a good time listening to your talk.
Thank you very much. And once again, I appreciate the opportunity to speak here, and really impressed by the organization and making this event happen. So thank you.
Well, thank you. Thank you very much. Have a good day.